Hey, hi friends. Good evening, everyone. Hope you're doing good. If you are in Hyderabad, make sure you are staying safe. Don't wander outside. It's gonna rain heavily for the next 1 week. The forecast says that, right? So you have to be a little careful and stay in house and probably study, right? So let's talk about the um, GIS systems. We are talking about geospatial analytics. And here we are talking about geospatial analytics with respect to various Python libraries. The data with where we will have locations mentioned. In short, any data where we have location, Earth, geographic location mentioned. That's called as GIS data or geospatial data. Now on the screen, we are looking at the standard analytics process that is generally applied. It's called as CRISP MLQ methodology. And we were discussing about the characteristics of geospatial data, the applications to start with, and then the characteristics of geospatial data. Then we also talked about various Python libraries and the data formats, which are broadly segregated into two categories. One is raster data, which is nothing but image data. And then we have vector data, which is like XY coordinates on the X and Y plane. And then we yesterday were looking at right some of the libraries and Python libraries and how to deal with them. So let us talk about some more important points with respect to geospatial data today as part of today's session. The first point that I want to talk about is with respect to the distance measure. So when we talk about geospatial analytics, right, the first is we need to understand the Earth models. Now, when you talk about Earth model, we basically categorize the Earth in, or we try to visualize or see the Earth in three different models. The geospatial analysis basically is talking about looking at various characteristics of the objects on the Earth. And in order to talk about that relationships, basically, we tend to see the distances to start with. Okay, that's the first thing that we need to look at that. But when we talk about measuring the distances accurately, it is not physically possible to do that. Right. And in fact, the Earth, as we know, right, can be modeled into these three different ways. First one is called as the flat plane. The flat plane is basically the world map that you see on a big chart, on a single sheet. Right? The entire continent, the entire Earth is basically placed in the single piece of paper. This is called as a flat plane. Right? I mean, we assume that the Earth is flat. That's how the historic events have actually started doing to look at the Earth. That's how it began. So it was assumed that the Earth was a flat plane. And in this case, when we are trying to calculate the distances, simple XY coordinate based distances, that is called as Euclidean distance or Pythagoras theorem, right? Pythagorean theorem. This is what is used for measuring the distances. Then later on, the other aspect that we look at is the spherical shape. When you talk about spherical shape, I mean, generally we talk about Earth being spherical, right? As a globe, circle, right? It's in a spherical shape. So for dealing with the spherical shape thing, we try and assume that data is spherical to begin with. And this is more close to the reality, right? So we try to model our calculations based on this assumption that Earth is round, a sphere. And of course, that is more close to reality. That's what we believe. Now, when you talk about spherical shape, the fact is we don't just look at the distances. It's not any more straight distance, right? It's a circle. So here we also have to look at the angles, right? Your Euclidean distance probably is not good method to be used here, right? Now, the advantages, of course, when you're trying to bring in the angles, the degrees, then the calculations also becomes a little right, tricky. But of course, it gives you a better accuracy compared to straight Euclidean distance method. Especially the distances are long, very large distances, then the sphere and flat, they tend to change, isn't it? If I talk about a circle, if this is circle, I'm bad at drawing. Okay, this is my circle. So from point A to point B, if I have to look at, then there is a circle shape, right? I mean, it's a 3D, imagine a 3D globe kind of a thing. Then you will see this kind of a shape. But if it is a flat plane, point A to point B is a straight line. So there will be differences. And in reality, this is what you see, right? So we are getting closer to reality. But we also have something called as ellipsoid distance measure. And this model is considered to be a better model to talk about the Earth surface measurements. And here the models use something called as a datum or geodic system, right? Now this datum or geodic system is, different types of geodic systems are there. It basically talks about a set of values that basically are used to define the shape of the Earth, right? In fact, the values are giving us the shape of the Earth, right? And we say that it does not have a constant radius also. And if I talk about a circle, probably you will say there is a radius, right? But when you talk about this geodic systems, we also say that towards the poles, to talk about Earth, it's a 3D, right? So here the radius will be different, here the radius will be different, here the radius will be different. So this is one of the default assumption that we look at. We say that the radiuses are not constant. Now this datum or geodic systems, there are different systems, as we said. The most commonly used system is called as WGS84. Okay, this is something that we commonly use as a global standard. There are many such standards. We have something called as NAD 83. This is another standard that we have. We also have European terrestrial. This is North America, NA, North America datum. Then, as I said, we also have European terrestrial datum, and that is called as ETRS89, European. So we will have different standards. Okay, that's basically something that you need to understand. Okay, and as I mentioned, it looks at this specific condition. The radius is not constant from the center. Next, when we talk about the distance calculations for these different models, I mean, the data that we have and we need to calculate the distances, then the distances can be calculated using two different methods. Here we are talking about three different formulas to start with. The first one is nothing but Pythagorean theorem, also known as Euclidean distance. And it is a very simple logic, right? I mean, you might have seen this Pythagorean theorem logic. To calculate two distances, we basically have a square plus b square is equals to c square. Triangle shape, right? If you have a triangle, we can generally see that. This is based on that distance measure. So we basically are talking about moving the data or measuring the distance with respect to two data points. So for example, if this is a x and y coordinate, only two axes assume x and y, then you represent the data point as x comma y. This is the coordinate, and I have another measure called x2, y2. Let's say x1, y1 and x2, y2. The distance can be measured using x1, x2. So this is the difference between the x coordinates. Similarly, on y coordinates, we have this distance, and we're capturing the magnitude. So we square the values, distances, and then add all the values. That gives you the distance between these two data points. This is the very, very popular, famous formula that we use. Next, we have something called as Haverson Formula. Now, we will be doing these calculations in Python, also very simple calculations. We will do that. And right, next one is Haverson Formula. Now, this Haverson formula is very important formula. It uses the great circle logic, great circle distance problem also. Right, a great circle basically is speaking about measuring the distances between 2 points. That is the shortest distance between 2 points. But this time it is a sphere. It is not a straight line. Right? Your Pythagoras theorem does not consider basically this. This is a problem because we're not having any straight line now. It is a sphere, so it will have curved distances, angled distances. Right? So that's basically your Haverson formula, and we will basically use degrees as input here. We'll also bring angles or degrees at which the data is connected into picture. All right. Next is something called as Vincenti's Vincenti's formula. Now, this Vincenti's formula is considered to be the most precise formula among all the three that we are talking about. Haverson itself is considered to be a better measure or a more accurate measure compared to your Pythagoras theorem or Euclidean distance method. But on top of that, Vincenti's are even considered to be more accurate. So Vincenti's logic, it considers your ellipsoid model of the Earth. That means it is basically talking about not just a sphere, but it talks about something like this. It's a sphere, but at the poles we will have crust, right? Something like crust, right? So this is ellipsoid model. One different models are there. One such model is this. Vincenti's theorem considers this as well. So these are the three different formulas that we can see here. And we can do the calculations using these formulas. Let us try and do the calculations here and try to see how each of this is giving us the results. So we will look into the distance measures formula. On the screen, what you're seeing is called as spider. I'm assuming you're familiar with spider. Spider is an IDE, which is known as Interactive Development Environment for Python. So underneath the IDE, we have Python engine. Now, IDE is nothing but a graphical user interface. So what you're seeing is a graphical user interface. And this user interface is allowing users to do the calculations that are fairly easier. So let us try and do this. All right, so let us calculate. The first one is Euclidean distance. So if you see, I'm trying to define coordinates here. Right, I have x coordinate and y coordinate. Right, and I'm simply doing the distance calculations. How do we do the distance calculation here? We are basically saying difference between the two values. X1, Y1, X2, Y2. So we are doing X1 minus X2. This gives me the x-axis difference. Y1 minus Y2, this gives me the y-axis difference. Then the formula that we are looking at is, let's say distance square is equals to x square plus y square. The distance on x square, distance on y. Distance is calculated with squaring that. So if your formula, if you see the formula, distance is equals to square root of, right, x1 minus x2 whole square, y1 minus y2 whole square. That's the formula. Okay, that's basically what we are trying to do. And when you calculate, you get distance square, and using library math, we are calling a function called square root, and we will be getting the distance. So I'm doing the calculation here, and I get distance as 240,202. So this is how we do the Pythagorean theorem implementation. Now, when we talk about radians, so when we bring in the spherical concepts, right, when we talk about degrees, decimals and degrees, right, you might want to convert that into a radian. A radian is basically nothing but your angle by pi. Right, 1 radian is equal to 180 degrees by pi. So you can in fact say pi radians, if I take this, this is equal to 180 degrees, straight line. Right, 90 degrees is this. So we're talking about 180 degrees, it's like a straight line. So pi radians is equals to a straight line, you can see. So we will be able to convert the data with respect to radians using the formula called math.radians. Right, so it is going to simply convert the degrees into radians. So the radius of the earth in meters is converted to radians basically here. So let us do this. So again, the same logic. I cleared everything and I'm generating here the radians. So we are calculating x1. We're defining x1 and x2, y1 and y2. Right, 2 data points, and then we are trying to measure the distances after converting the values into, After the distance, we're converting the value into radian, x-axis, y-axis. And then using the radians, we are doing the calculation, and we also do the multiplication here. Yeah, so we are getting this number, 251 kilometers. Okay. Then if I talk about Haverson formula, then this is basically the formula for Haverson. Let us remove that. So I'm importing the library math, and then I'm defining my x-axis, the first data point coordinates x1, y1. Then I'm also defining x2 and y2. So we have x-axis and y-axis values for 2 data points. Now I'm calculating the distance first, converting the values to radians, right? And then we're also trying to do the calculation on latitude. Y-axis is basically being also y-axis, which is latitudes, right? We're converting that latitude coordinates to radians directly by 1 by 2. Y1, Y2. Using these values, I'm applying the angle, the calculation here. A is equals to sine theta, right? Value square plus, again, we have x distance, right? Whole square by divided by 2 whole square. Then whole divided by, we are talking about your multiplied by cos radian calculations. So this is the formula. And when we write the formula, when we execute this formula, let's just directly execute this. And then we are doing the sine on the square root and 2. This is the formula. And we are converting this into the kilometers. So we get 240 kilometers. So previously we got 240.2 kilometers. Here also we are getting 240.6 kilometers. So this way we can do the distance calculations. We will also be able to use radian formula here, right? Or Haverson formula, or directly we can go for Theorem. Then if I talk about Vincenti's formula, right, it is basically having a lot of calculations. Code is large, and the code that we are talking about here is basically using an ellipsoid called NAD83. That's North America's datum, which was defined in 83 as a standard. So using this ellipsoid, we are doing the calculations. So again, let's remove this. So to start with, we are saying distance is none. That means there is no value. And then we have x-axis, y-axis, coordinates for the data points, x1, y1, x2, y2. Next, these are all standard values. We have a semi-major axis. I'm defining that as A. Right, and then we are also doing flattening here. This is standard numbers. We are doing the flattening. So I have F also calculated, and this is the semi-minor axis. Then we are calculating radians of the difference, x2 minus x1. And then we are calculating the tan, a tan basically, This is I'm calling as U1 and U2. Then using this U1 and U2, we are calculating the sine and cosine values for U1 and U2 both. Then I'm defining Im as L. This is basically nothing but value, where we have calculated right, L here as the radians. I'm defining that as L. So the whatever the value that you have, right, for L, that is assigned to Im. Right, you can directly use L also here. If you don't want to use lam, you can directly use L. So sine, cosine, sine sigma. We do the calculations here. This is a for loop. All this while till here we are doing the calculations. Right. So all this is the code that we try to execute here. And then we try to do some more calculations. Cos square alpha is something that we're doing. This is B, and delta sigma. This is a mathematical calculation again. And then we are trying to pursue this. And finally, we get the distance. So 240, basically 240.1 kilometers, you can see 240 kilometers. If I run this entire code once again, I get 240 kilometers. So this is how we measure the distances between the values, different values that we have. Next, we will be doing some more calculations here. One of the calculations is to look at the projection. We call it as reprojection. And basically it is used for looking into data distribution ultimately. We have different advanced data distribution, so we don't look into reprojection related tasks. Now, when you want to implement this, we will have the OGR Python API that we have seen yesterday, that's required. And we also have something called as OSR, which is Open Special Reference Module. These two are required here. Right, so let us look into the code. Reprojection. No module called process OSR. So click install. OSR. Let's see if it works. Otherwise, we will have to do this calculation from Google Colab. Okay, there is another value that you might want to look into Google Colab. We'll be doing that. It's basically it could be a different library altogether. See, it's not working here. So let's move on, and we'll talk about some interesting points as well. Now, whenever we talk about geospatial data, we basically look at two different scenarios. One is the vector data, the other one is raster data. Raster data is nothing but the image data. So whatever we have seen the data till now is more like a vector data, where we used data to measure the distances. Right now, using the raster data, we will do some kind of a small hands-on here. A heat map will be generated, and this heat map is basically going to show the clustering of the data using the raster image. right? Or in short, an image. Now, on the geographic image, we are trying to identify the intensity factor. We have a data set which is in the tabular format. We call this as bare-sightings.csv. This is available over online. You can download this data. Right, and we are trying to look at the bare sightings. Right, and we are trying to visually represent that on a map. Right, a heat map is basically being plotted. You can see that heat map library at the top. Right, and this basically is a Mississippi, right? State of Mississippi in US, right? That data. As I said, it is a publicly available data. We're doing it. The heat map that we are going to get is going to be stored in the local. When I say local, HTML file, you'll be able to download the file from Google Colab and then work on this. So this is a Python environment that you're seeing, which is provided by Google. Bare sightings. So first thing we do is import Folium library. Once the library is installed, you import that Folium and also a plugin which is going to help us to come up with heat map. Still executing. Done. So we have the file executed. Then, in order to work with this data, it is a Google Colab. So it is a remote server which is given by Google Platform, GCP. But in order to work on offline data, we need to load the data first into Python. Now, Google Colab cannot directly access your folder. So we need to put the data into the folder. Right. So every time you reinstall your server, you will see this screen. Right. And here we will be loading our data. So let us load the data. You click on this. And we are basically going to data bare sightings underscore sightings.csv. Okay. So yeah, you can see that CSV file is stored in the system now, a remote system. And whenever you close this remote system, automatically or release the servers resources, then automatically the data that we are talking about is removed. So we are using open function and read the data as is. We're not using third-party libraries, which will try and convert the data into structured format, but rather we are using open function. Now, in order to get the location, we say here on the data, right click and say, left click on the file, left click, and then say copy path. So once you have updated the path here inside the open function, you're going to look at read mode. Yeah, the data is now in read mode. So we are loading the data and reading the content of the data into lines. We're removing the Pop 0 basically is going to remove the first observation, which is there in the index is 0. So once that lines are clean, then we are creating an empty list called data. And then I'm also saying bears. We're using strip function to capture multiple values. So each value we are trying to, we are trying to select and then capture the values. Done, executed. So I have my data, I have bears. Right, all these data are there. Then we are trying to map here. So M is basically the coordinates, and we are trying to talk about the zoom options and right, all these UI respective. Then the heat map, we are basically talking about the data, right? And then we say max zone is equals to 60. Now, once we are able to execute this, we will be able to see the heat map. And that heat map will have to be saved into a HTML file for us to actually see it, right? Visually see this data. So when you executed this, the data is getting saved here in the pane in the folder along with the folder. So if I want to see this, I'll download it. Right, I get a HTML file and then we click. So you can see all those areas, right? Darker the area, more intensity, the bare areas. Okay, those are the locations where the bears are actually doing the routes. So we have successfully represented the data on a map. So this is one such application that we have with respect to the GeoSpatial data. And here we are talking about heat map. There are many such applications. In our next class, we will be discussing about one such application which involves unsupervised learning technique. Under that, we have clustering. Clustering or segmentation. Now, this clustering or segmentation is basically done right in such a way that we take the values which are close together into one group. We consider all the values which are there in one group as one segment or one cluster. The characteristics of all the data points within that group will be similar. Okay. Now, how do we do clustering? What do we do? Right. We'll be explaining that now. Clustering is an basically a topic under unsupervised learning. That means we will not be able to do any prediction. Right? We're not doing any prediction. Under this unsupervised learning, we have the clustering or segmentation. And when you say clustering or segmentation, the one primary focus is that we need to get homogeneous records into one particular case. Homogeneous record. We also will have heterogeneity. The heterogeneity basically speaks about difference or variations in the data. Now, clustering is a topic which tries to measure the distances and then take a call on whether they are homogeneous or whether these data points are heterogeneous. And this clustering can be broadly done in two ways. Broadly, right? It's not refined to only these things. There are many other, but broadly we see the clustering exercise basically implemented using hierarchical clustering or non-hierarchical clustering, the second option, which is also known as partition-based clustering. So clustering topic is measuring distances. We discussed about distances. It is going to measure the distances between two data points and then declare whether those points are similar or not. Right, so that's about your hierarchy or non-hierarchical clustering, or in short, it is clustering exercise. But this clustering exercise is also now divided into two types. Right, I mean there are many, but these are the broad two types of clustering techniques that we should be able to speak about: hierarchical and non-hierarchical. In hierarchical clustering, there is a natural repository. When we say natural repository, we are speaking about some contracts or something of those lines. Here we will have to basically visually see the data using something called as dendrogram. Dendrogram is nothing but a visual representation of the flow diagram that we basically are coming up with hierarchical clustering. Dendrogram. So it's a visual representation of the grouping that we basically are having. And as I said, there are different libraries that you can look into with respect to distance calibrations. But we will stick to this dendrogram. The one thing that you need to look at is in clustering, we have dendrogram and we also have K. But whereas if you talk about non-hierarchical clustering, we will have K, of course, but along with that, we also have the logic that the distances are based on some random reason. Distances are measured with respect to random initial partitions. That's your K means 6, or also known as non-hierarchical space. As the name says, it is K means, right? Or basically, we're talking about non-overlapping clustering. So predefined K will be there, whereas here we don't have predefined K value. We have to manually give the clustering labels. But in hierarchical clustering, we will be able to see the result also. Right, so we have hierarchical clustering and non-hierarchical clustering. The advantages and disadvantages. In hierarchical clustering, there is explainability. Right? And there is no dendrogram, of course, but it is good for large data sets. So not so good for large data sets. If we talk about non-hierarchical clustering, here, these are specifically good for large data. And explainability of the clusters, the end results is not possible here because we'll start randomly, right? And this may lead to different results. Now that's the disadvantage with respect to non-hierarchical clustering. Ultimately, what we are trying to do is, if this is my data, this data is spread like this. So we are basically trying to group the data like this with respect to their similarity in the data. But we start randomly probability, right? The initial stage. Right, we try to measure the distances and then we will group the data points. But clustering is all about right, hierarchical or k-means. It basically talks about how well the clusters are formed. Okay, we are trying to do a measure on how well the end result, the clusters that we are obtaining are given. Now, these clusters will be considered to be a successful grouping when you don't see a dissimilar. You don't see a dissimilar record. Do not see. That is important. Not to see. So we are trying to group the data in such a way that all the similar records fall in this group, all the similar records falling in this group. So when your data points are grouped like this, then the characteristics are also same. Based on that only we are trying to group, right, the data. Now, to do all these things that we are basically talking about, finding out the similarities, finding out the dissimilarities, dendrograms, no dendrograms, right? All these things can be done using Python. That would be our next class. On Monday, we will be seeing how clustering can actually help a business problem. Right, and we try to group these locations or strategies and create one cluster. Right, and we are trying to evaluate on whether the values within that cluster, whatever the values that are found, are those right values basically accepted or not. Right, so we are basically talking about, again, once again, if I have to summarize, we are talking about GIS data, right here, GIS data. And whenever we talk about GIS data, it has to be locations. And the data is broadly categorized into raster data and vector data. We have looked at different file formats, including the tabular formats, TSV, CSV, spreadsheets, JSON files, right? GeoPandas, GeoJSON, so on and so forth. Different formats are there, shape files, right? These formats, depending on what data they carry, they can be categorized into raster data or vector data. Right, so that is about your data. And then we have specific libraries. And we also have specific file formats. One visualization, one raster-based data that we have used is bare sightings. Using that data, we try to come up with heat map. Then for vector data, we basically talk about XY coordinates. In our next class, that is on Monday, we are going to talk about vector data. And then we will be using this vector data and try to implement a solution for a business problem using the analytics technique called clustering. And clustering is nothing but grouping of similar data points into one cluster. So that's about the scenario for the day. Right, and basically we have seen the heat map. Let me again go there. And if you see this, it basically speaking about right, the areas where the bear findings are there, where are bears are cited. All right, so this is about your leaflet with maps, right? And it is generated in a HTML. And we are trying to use different colors to talk about this. All right, so that's it for the day. We will be looking into different examples on Monday. As I said, clustering is something that we will be doing. And we'll also try and look into different other use cases as well. All right, with this, I'll conclude for the day. And once again, stay safe. The rains are heavy. Take care of yourself and enjoy the weekend. We'll connect on Monday. Thank you, everyone, and bye.